So feel free to unmute yourself, and then if you want to ask questions or anything, that would be really great. So then I'm not just talking to myself the whole time. Actually, I forgot the first slide is written stuff. So before we start reviewing, I wanted to see if anybody had any questions, and then if you do, I'm going to type out the question so I can answer it on video later as well. Does anyone have any questions just about like the final exam or anything related to the end of the semester? No? Okay, that's fine. Okay, so on this first page, we're gonna start with benzaldehyde. And we're just gonna crank out a couple different reactions. So go ahead and take, just like take a minute and try and figure out some of these if you can. If there are ones that you don't know, just go ahead and skip them for now. But if there are ones that you do know, go ahead and try to write it out. And I'll also post a blank version of this probably in the middle of today. Okay, so let's start at the top. If I react benzaldehyde with potassium permanganate, what's going to happen?
Is that the reduction? The reduction where it'll turn into an alcohol?
No, you're going the opposite direction. So it's not a reduction, but it is an oxidation. Does anyone know what the product's going to be? Usually you also see this as an aqueous base solution. Okay, yeah, I see in the chat oxidation of the side chain to carboxylic acid. That's good. That was from Addison. So potassium permanganate is one of our strong oxidants. So it's going to turn the aldehyde into a carboxylic acid. What are these conditions here? Does anyone recognize the reaction? It won't let me erase that. Why? Okay. Does anyone recognize the name of the reaction or what's going to happen? Yeah, so Addison got it again. This is a Wolff-Kishner reduction. What is the product going to be? What does Wolff-Kishner do? Y'all can unmute yourself and answer out loud if you'd like. Nobody? What?
It's going to reduce the carbonyl.
Yeah, we're going to reduce it to what? What's going to be left on the benzylic carbon? There, I can kind of hear that somebody is saying something, but I can't hear what. That's okay. So with Wolff-Kishner, you first react with hydrazine and you end up making a hydrazone. And then with the potassium hydroxide and heat, you end up reducing it. Why won't it let me draw? There it goes. To the point where there's just nothing there. So it just completely eliminates the carbonyl. So in the place of the carbonyl, you'll end up putting 2 hydrogens. And then here's our original hydrogen. So this would turn benzaldehyde to toluene. What next? Does anyone have an answer to any of the remaining problems? Let's go to the left. What happens when you react an aldehyde with a Grignard reagent?
Does it add what comes with the Grignard?
Yeah, so the Grignard is a nucleophile, right? So these electrons are essentially focused on this carbon, and they're going to attack the carbonyl carbon. So here's our carbonyl carbon. It would have an O minus, but then in the second step with the water, we're going to end up protonating it. So it would turn into an alcohol. Our hydrogen would still be there. And then our 2 carbons that we just added. So with the Grignard reagent, always be really careful. Make sure that you're adding the right number of carbons. So there's 1 here and the second one here. 1, 2. Does that make sense?
Yes.
What about this arrow here? What is this one doing?
Is that one kind of acting kind of like Grignard because it attaches that also?
Yeah, definitely. The first step is kind of like how Grignard works, but this reaction goes a little further. Does anyone remember what this is? Does the term like phosphorus ylide ring a bell at all?
Doesn't it create an alkene?
Yeah, we're going to create an alkene. So we can go through the mechanism of this later if you guys want, or you can see the mechanism back in, I guess it was chapter like 16 or something. But essentially, this ends up creating an alkene where the carbonyl had been. And the alkene is going to be to this carbon. So that entire like chunk of carbons is going to get put on here. Does anyone remember the name of this reaction?
Wittig reaction?
Yeah, this is the Wittig reaction. So if you're not sure about this one, definitely look it up and review it. Okay, and this next one, we have an aldehyde and we're reacting with hydrogen cyanide. What do we know about cyanide? Like usually we see cyanide written out with sodium as a counter ion. And why are we usually using cyanide?
It's a good nucleophile.
Yeah, it's a nucleophile. In the case of hydrogen cyanide, it's not an ionic compound. This is an acid. And it's not one of our strong acids, but it's not really weak either. So in the first step, we would end up protonating the aldehyde. And then what would happen with the cyanide? So I know I haven't been drawing out mechanisms or anything, but let's say we have this protonated aldehyde, and we also have cyanide. What's going to happen?
Is it gonna attack the carbonyl?
Yep. It would attack the carbonyl. And that's our product. This is a cyanohydrin. Okay, and then last one, we have a primary amine, acid, and an aldehyde. What is this setting us up for?
Is it going to create an amide or an amide?
Not an amide, but it is going to create something amine related. So an amide can be formed from a carboxylic acid. But what happens when you react an amine with an aldehyde or a ketone? This is from the same part of the chapter when we first learned about Wolff-Kishner. We didn't immediately go into making hydrozones necessarily, but this is very similar.
Does it create an amine?
Yeah. So when you see an aldehyde or a ketone and a primary amine, you should immediately think amine. Are there any questions about this page? Okay, y'all are okay?
Yes.
Okay. Okay. So this is basically just taking one carboxylic acid and turning it into a bunch of carboxylic acid derivatives. So there are a couple ways to do some of these problems. So we're going to try and come up with as many as we can. So to go from a carboxylic acid to an ester, what is one way you could do that? There's a named reaction that makes esters from carboxylic acids.
Is it the Fischer esterification?
Yeah. What's the reagents for that? I guess what are the reagents? Anybody?
Isn't that one where it's either an acid or a base?
So Fischer esterification is done in acid usually. We could make it with a base. Emily is suggesting acid. So yeah, we definitely want acid. What else do we need with the acid to make this happen?
And alcohol?
Mm-hmm. So this one is which alcohol? What are we going to use?
Ethanol?
Yeah, we're going to use ethanol. And how much ethanol do we need? Do we need one equivalent?
Needs to be in excess, right?
Yeah, it needs to be in excess. So usually you're taking your carboxylic acid and you're dissolving it in ethanol and adding in acid as a catalyst. Sorry, the way I wrote this looks like we're gonna come up with, like, it's a multiple step process. It's not. This is one way that you could make an ester. What's another way that we could do this? How about we come back to that? Let's look at the next line. Carboxylic acid to acyl chloride. What's the only way that we know to do that?
Mm,
What's the name of the reagent?
Thionyl chloride?
Yeah. Okay, and what's special about acyl chlorides?
They can be used to make carboxylic acid derivatives.
Yes, because they're super reactive. So in the problem above, if we reacted with thionyl chloride, what could we react with in step 2 to get to the ester?
Wouldn't it just be ethanol?
Yeah, you could do ethanol. It would be even better if you just did ethoxide, because then you wouldn't have to worry about deprotonating an intermediate or something. Okay. How would we make an anhydride from a carboxylic acid? Anybody?
Wouldn't you use like a carboxylate salt or something like that?
Well, so the carboxylic acid itself is not reactive enough to just like add in a carboxylate salt. But you could react with thionyl chloride first and then add in your salt or even just another equivalent. You could also add in like less than one equivalent of thionyl chloride. Because then once you do that, you're going to create some of your acid halide and you'll still have some carboxylic acid. What else could we do? There's one way to do this that doesn't require any reagents at all.
Just heat it up.
Yeah, you could just heat it up. So heat and possibly needing pressure. There are also some acids you could use, like heating it up with phosphoric acid would work. And then there's some drying reagents that I don't think we covered. So we don't need to worry about those, but all of these ways would be acceptable ways to make an anhydride. Okay, and then last one, to get to the amide. Amides are pretty tricky to make, but they're very stable. Can we go from carboxylic acid to amide in one step?
No.
Yeah, not really. Like you could, but your yield would be really, really low. So what would be a better way to do it? So the carboxylic acid is not reactive enough to just react with an amine and get to the amide. Is there something else that's more reactive?
Maybe if you broke down the carbonyl and then the oxygen was negative, then it would make it more reactive.
Well, so we want to be able to displace the OH group though. And if we deprotonate it, it's going to be even harder to displace. I was looking for, turn it into an acid halide, right? And then just add in an excess of the amine. So at least 2 equivalents. Why do we need an excess of the amine?
To deprotonate
Yeah.
the, yeah.
Yeah, exactly. So when you first react with the acid halide, you're going to have a protonated version of your product. And so you need another equivalent of the amine to come by and deprotonate it. Okay. Are there any questions about this page? Okay, cool. Okay, so we have some multi-step reactions here. Nothing too crazy though. Oh, I just saw a mistake in my bottom one here. I did not want that to be a carboxylic acid. I want that to be an aldehyde. Okay, so top one, we have benzoic acid, and we're reacting with an excess of alcohol in acid. What are we doing in that first step?
Creating an ester.
Yeah, so this is Fischer esterification, just like we saw on the previous page. So after step one, whoops, I did not mean to reverse. Okay. After step one, we would have an ethyl ester. And then in step two, we're adding in another ester and also ethoxide. Why would we do that? What's going to happen with the ester and the ethoxide? What are these two reagents together making?
An enolate.
Yeah, exactly. So we're going to deprotonate at the alpha carbon to get our ester enolate. And what's going to happen with that? What type of reaction are we setting up here? What type of reaction uses an ester enolate in a reaction with an ester?
Does it create the beta keto ester?
Yeah, so this is a Claisen condensation. So we're going to make the beta keto ester. I'm just going to draw out the basic steps of the mechanism because I'm not sure we're all following at this point. So we added to the carbonyl carbon of the original ester. And this carbon right here is our enolate carbon. So we want to make sure that all the right stuff is hanging off of it. So we should have our ester, and then we should also have 1, 2 more carbons. So this is our intermediate structure. What's going to happen from here?
The carbonyl bond is going to reform and the ester will be, or the ether will be kicked.
Yeah, so we reform our pi bond and we kick out the ethoxy group. And that gives us our beta keto ester. Does anyone remember what happens after this? Because we get to our product, but then we move away from our product before we can come back to it.
The ethoxide that you just made, or the ethoxy group, comes and deprotonates it in order to form the driving force, right?
Yeah, so we have another proton here, and like Daniel said, the driving force of this reaction is forming another equivalent of ethanol by deprotonating. So this always, it seems kind of silly that you would, make your product and then deprotonate it, but this is what's actually driving the reaction. And it's important to remember that this occurs because if you don't have a proton here to pull off, the Claisen reaction is unlikely to occur. And so after step 2, this is actually kind of your product. And then in step 3, we introduce ethanol again, so that we can protonate it again to get to our beta keto ester. So remember, this exam is multiple choice. You're not going to have to draw out mechanisms or anything, but there are questions about, driving force of reactions, about, which step is going to happen, or, which step in the mechanism is important, or what intermediates are important, things like that. Are there any questions about this?
So for this question, the ETOH, that was the driving force.
Right. So when we produced this equivalent of ethanol in this step up here, that's the driving force for the reaction. It's the formation of the weaker base because this proton that we pulled off probably has a pKa of like 9 or 10, but the pKa of the ethanol is 16. So it's that acid base interaction at the end that drives the reaction. Okay, I'm going to erase some of the extra stuff here and just leave the image of the product so that we have some room to work out the next problem. Okay, because it is going to take a little bit of space. Okay, so we're starting off with an aldehyde and we're putting it into sulfuric acid and heat. We can't assume that there's water around because it's not indicated, so this must be concentrated sulfuric acid. What type of reaction is this doing?
Is that sulfonating? Or
So for sulfonation, you would need a benzene ring. This is not aromatic, it's just an aldehyde. We have dehydration as a suggestion. Not quite. There is going to be a step that is kind of like dehydration in here. Think of chapter 18. What was one of the big topics in chapter 18? Maybe it was 19. Does aldol condensation sound familiar? Anybody? It's hard to tell if y'all are with me because nobody's saying anything and all of your cameras are turned off. So I'm just kind of hoping that we're all on the same page here. So when you see an aldehyde or a ketone and no other organic reagent, and you have an acid or a base, just go ahead and excuse me. Just go ahead and assume that it's aldol because it's going to have to react with itself. So with that hint, go ahead and take a minute while I drink some water because I'm apparently dying over here. Try and come up with the aldol condensation product on your own. And then if you get to that, try and move forward in the reaction. Okay, what type of compound is the product of an aldol condensation?
Isn't it an alpha beta unsaturated ketone?
Yeah, an alpha beta unsaturated ketone or aldehyde. In this case, we're going to have an aldehyde. Do I need to go through the mechanism of this?
Is this the one where it turns it makes this hydrogen go into a double bond after it's taken?
Yeah, yeah, I'm gonna go ahead and create a new slide and we're gonna go through the mechanism of this real fast. Just because I didn't hear a lot of recognition of this initially. Okay, so what is the first step in an aldol reaction? I mean, okay, so we're an acid. What's our first step, period?
To pronate?
Yeah, we have to protonate something. Okay, and then what else do we need to do for an aldol reaction to occur? We're going to end up reacting with two equivalents of the aldehyde, right? one of the equivalents has to be turned into something reactive.
So is that carbonyl? Or is it the oxygen? I'm confused.
Not the oxygen. Does drawing in this hydrogen help?
Yes. Oh,
Like we need to make a nucleophile out of this compound. What's our nucleophile going to be?
Enolate.
Not an enolate because we're an acid, but we are going to make an enol. So you can use the conjugate base of your acid, whatever it would be. Since we had sulfuric acid, hydrogen sulfate would be our conjugate base. So now we have our enol, and we have our aldehyde. We're going to go ahead and keep it protonated because we're an acid, so all the aldehyde in this reaction mixture would be protonated. And for this to attack, we're going to reform the pi bond between the oxygen and the carbon, and we're going to push out the pi electrons to attack the carbonyl. Does that make sense so far?
Yes.
So I'm going to use two different colors to keep our equivalents of aldehyde separate. So this is the aldehyde that did the attacking. This is the new bond that we just made. This would be the carbonyl carbon of the aldehyde that we attacked. That's going to have an OH group, a hydrogen, and it's going to have this whole carbon chain coming off of it. So that's 1, 2, 3, oops, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right. So that's our intermediate so far. This is the aldol addition product, or at least it will be once we deprotonate. Okay, so this is our aldol addition product, but we're not going to stop at the addition product. How do we know that we're not stopping here?
Because heat is added.
Right. So the presence of heat tells us that we're going to go all the way through the condensation. So what's the first step here for the condensation to occur? What do we need to get rid of?
Won't the other alpha hydrogen be deprotonated or removed?
Yeah, we're gonna have to pull off the other alpha hydrogen. But when we do that, what else are we gonna be kicking out?
The OH.
Right. And since we're an acid, can we just kick out the OH group?
No, it'll have to form water, right?
Right. And how can we do that?
By protonating it.
Yes. Remember, when you're an acid, if you want to get rid of an OH group, just protonate it, and then you're like halfway there. Okay, so then what happens next? We protonated that OH group. So what is it going to do now?
It's going to take its electrons and leave.
Exactly. I love the way you said that. Okay, so now we have a carbocation on that carbon, on the beta carbon, and we also have water. What do we need to do next?
Now water can remove the alpha hydrogen,
Perfect.
forming the double bond.
Yep. So the electrons that are in that bond are going to come down to form the double bond. And now we have our condensation product. So we're gonna have a double bond there. Okay, are there any questions about that? Once you understand how this works, there's actually kind of a cute shortcut for coming up with the product. It's just you have to know how it works in order to get there. If you draw the aldehyde and then draw it again, but in the place of the oxygen, put the alpha carbon, basically, of your other one, you get your product. So then you can just erase that oxygen and you'll have it. But you have to understand how it works in order to be able to picture that. But that'll speed you through the whole process.
So I have a question.
Mm-hmm.
If we were in base, then the alpha hydrogen would be removed first, forming a double bond, and then kicking out the OH group, right?
Right, all in one step. So that mechanism is actually a lot shorter. So I have no problem showing all that real fast because it doesn't take very long at all. So if we were doing this in base instead, we would start off by simply just removing the alpha proton to create an enolate. I'm going to draw the carbanion form. And then you would attack another equivalent of the aldehyde. So this would be our original aldehyde coming back. Here's the new bond that we would have just created. 1, 2, 3, 4, 5. And we'd have an alkoxide ion there. We would protonate using the water that we would have made initially in this reaction when we created our enolate. So this is our addition product. And then in the last step, since you're already in hydroxide, there's no reason that you can't make another equivalent. And so you just kick it all out. You could also argue that this goes through more of an E1CB mechanism, but that's not really a mechanism that we cover here at Texas State, so we don't really bother with it. In the E1CB mechanism, essentially you just create an enolate as your intermediate here. You would deprotonate first. Ooh, that got ugly, sorry. and then use the electrons to push it out, but it's the same idea. Does this make sense?
Yes, thank you.
Okay, so after step 1, we would have our aldol addition product. Okay, so then in step 2, we're introducing sodium cyanide. What is that going to do? What is cyanide?
It's a strong nucleophile.
Yeah, it's a good nucleophile, but it's not particularly strong. Like if you compare it to like a Grignard reagent, it's not strong.
Okay.
And that's an important distinction only because of this reaction.
Isn't
So
it going to into the double bond right there?
yes, by double bond, what do you mean?
Like to form the conjugated product, right? It's going to add to like the.
Yeah, exactly. So this is going to do the 1,4 addition, right? The conjugate addition. So that would bring us ultimately to an intermediate here. And that's why we introduce water to the reaction, is so we can protonate that to get to our product. I don't have a lot of space, so I'm just going to draw the product by erasing the enolate. Okay. Does that make sense?
So in order for 1,2 addition to occur, it would need a strong nucleophile like a Grignard, right?
Right, yeah. Grignard is really the only one that we looked at that would add to the carbonyl carbon.
Okay.
Yeah, so cyanide, enolates, amines, all of these would add to the conjugate position. Are there any questions about this slide? Okay. So for slide 8, I wrote out a synthesis. This one kind of uses a lot of OCHEM 1. So I think for this one, the easiest thing to do is to work backwards. We're starting off with a 6-membered ring and ending with a 7-membered ester. What must be the last step of this reaction? There's only one way that you guys know to make a cyclic ester like that.
I got a question like regarding to like the final.
Mm-hmm.
So if we had a synthesis problem like this, would it just give us like multiple choice, like different ways to do it? Like, oh,
Yes.
1, 2, 3, and then another 1, 2, 3.
Yeah, so yeah, it would be like, here's a bunch of different syntheses, which one would work. Mostly, I can't remember, I don't think we really put any synthesis problems on there. It was mostly like, here are some reagents, what's going to be the outcome. And once or twice we did like a product and an original reactant with a blank reagent arrow, but we provided the reagents and none of them were really complicated syntheses. Courtney, I see your question. It'll be uploaded, I guess, as soon as it's done downloading, so probably by noon. And yeah, office hours are technically over, but I'm just gonna keep going if you guys want to stick around. I don't mind. Any thoughts on this?
This is a total guess, but can it be made from a dial?
I can't think of a way that you'd be able to do that. Okay, sorry, Courtney asked another question. For the practice saplings, they do not have to be 100% complete for you to receive extra credit. You'll just receive a portion of the extra credit. So if you end up with a 90% average on all of your practice sapling homeworks, you would end up with 4.5 points added, because that would be 90% of 5 points. And you only have to do the original practices, the ones that say practice 2. I just opened those because there were some people telling me that, like, they did chapter 12 and 13 at the beginning of the semester and they wanted to be able to do it again. So those are not worth points. They're just there for you to practice if you wanted more homework. Okay, any thoughts on this one?
This isn't a thought, but more like a question.
Mm-hmm.
How are we supposed to make this reactive, I guess? Because that looks pretty fine, like where it's at.
The ester?
Yeah, because you said we were working backwards, right?
Yeah, so what I want to know is, how could we have made this? So not what reactions could we do with it, but is there a way that we could have made it? Keeping in mind that this is your starting material, right? I mean, we could start at the beginning. What is in the original material that's not in the product?
And alcohol.
Yeah, we have
And
an
double bonds.
Yeah, and the alkenes. You could go ahead and get rid of the alkenes right now if you wanted. They're not going to help us get to the product. What could we use to get rid of the alkenes to hydrogenate them? Now, this is OChem 1. This is kind of a mean question, but you do have to be able to do this.
H2 and a catalyst?
Yeah, so hydrogen, and then essentially pick your favorite transition metal. Palladium is definitely the most common. And that would give us something without those double bonds. Is there anything that we could do to the alcohol to get it to something that could actually be turned into the ester? Miguel, I see your question, but I'm not sure what you mean.
Could you oxidate it to a carboxylic acid?
We couldn't get it to a carboxylic acid because it's a secondary alcohol, but we could oxidize it. If we used pretty much any oxidant, we would get the same outcome. What would that be?
A ketone?
Right. So any oxidant, you could do Jones, you could do PCC, you could do chromic acid if you wanted. You could use the Swern oxidation. I'm trying to remember all the ones that we use. I can't think of all of them, but any of those would give you the ketone. And then the ketone can actually be converted to the ester in one step. Well, that was a crazy arrow. What's the one step? What reaction inserts an oxygen between a carbonyl carbon and its alpha carbon?
Is it MCPBA?
Yeah, if you use MCPBA, you'll create an ester. This is the Baeyer-Villiger reaction. Cool. Any questions about that one?
So the Baeyer-Villiger reaction, is that mechanism going to be really important?
The mechanism, no.
Okay.
But the reaction, yes, I believe it's on the final exam. Okay, next synthesis problem. Any ideas? I actually have like 5 different routes written out on my paper. This is actually a problem I wrote in grad school when I was helping teach an organic 2 class. So first we have to kind of look at, where these carbons are ending up in the product. And there's a couple different ways that you could look at it. You could number these 1, 2, 3, 4. And you could have 1, 2, 3, 4, or you could have 1, 2, 3, 4. So a couple different routes, but I'll take just one. Somehow we're going to have to add on 2 more carbons. What's a good way to do that? What type of reagent do we often use when we want to add more carbons?
A Grignard?
Yeah, a Grignard. So if we used a Grignard with something, we wouldn't immediately get a ketone, right? What would we get instead?
And alcohol?
Yeah, so let's say that we somehow managed to make this alcohol using Grignard reagents. How could we oxidize it to the ketone?
With any oxidizing agent?
Yeah, like pick your favorite, right? They would all work. Okay, so how could we make that alcohol? We know that we have to have a 4-carbon piece and a 2-carbon piece because we're starting off with 4 carbons. So the question is, are we making this bond or this bond? A or B? Which one could be made using a Grignard?
B.
B, right. So what would we have to react with a Grignard to do this? So our Grignard would have to be a 2-carbon Grignard. And we'd have to follow it up with water to get to our alcohol. What would we be reacting with that Grignard? You can describe it to me or give me the IUPAC name. So right here is our Grignard. There's also a hydrogen on this carbon. Y'all can do this.
aldehyde?
Yeah. So you could use butanal. And the reason that we know that this is the answer is because here's our oxygen, here's our hydrogen, and here's our 3 carbons, right? When that Grignard attacks the carbonyl carbon, those 3 things still have to be attached to the carbonyl carbon. So you just kind of have to mentally subtract out the Grignard and you're good. Okay, how could we have made that aldehyde? Let's try going forwards. From an alkene, how could we add on some oxygens? What reaction would we have to use? Or what product are we aiming for? What functional group? Y'all are so close. You're really, really close.
Could you add HOH across the double bond?
Yeah, what functional group would that make?
A primary alcohol?
Yep. So if we have a primary alcohol, how can we turn it into an aldehyde? What reagent would that require?
Would it be something like PCC or something that oxidates?
Yeah. Yeah, no, it'd have to be PCC, right? Any other oxidizing agent would turn it into a carboxylic acid, or it could be SWERN, PCC or SWERN. All the other ones would turn it into a carboxylic acid. Okay, so to get from an alkene to a primary alcohol, what reagent do we have to use? Can we just add aqueous acid and get the least substituted alcohol?
No.
No, this is an anti-Markovnikov hydration, right? What do we have to use to get the anti-Markovnikov product?
Is it through hydroboration oxidation?
Yeah. So borane THF complex with hydroxide and hydrogen peroxide. Okay. Does that make sense? Are there any questions about this synthesis? Okay. Oh, okay, this is a long one. So let's come up with the products first, and then you can do the mechanism on your own time, and I'll also record myself doing it later. But I don't want to bore you guys right now because the last slide has a lot of stuff on it. So I want to make sure that we get through it without completely losing you. So in the first step, we're adding in, we have a ketone and we have a secondary amine and acid. What functional group are we making?
An enamine?
Yes. Also, whoops, I got ahead of myself. It's important to note that, all semester I've been saying to think of your reactions, in broad terms, like in terms of functional groups, the way that I just phrased the question a second ago. And apparently the other faculty agree with me, and that's actually the way a lot of questions are phrased on the final exam. is you have this functional group, and this thing. What functional group is formed? Okay, so that's step 1. And then in step 2, we're adding in an alpha beta unsaturated carbonyl compound. What is this?
Isn't it a Michael addition?
Yeah, so it's a Michael addition, and this is the Stork enamine reaction. So you should definitely write out the mechanism for this at some point. I'm just going to show you how the connections are made. The end product here for step 2 is going to be this iminium. This would be the bond that was just formed. And it's going to be attached to the other 6-membered ring. This is going to be really ugly. I'm so sorry. And then here is our carbonyl, right? I'm going to redraw that. I hate it so much. So this would be the product after step 2. And then in step 3, what are we doing?
The amine turns into a ketone.
Right, so this is the hydrolysis of the iminium ion that was formed. So this is the reaction that you want to look up if this doesn't really ring a bell for you. So step 1 is enamine formation. Step 2 is a Michael addition. Step 3 is hydrolysis of iminium ion. Okay, are there any questions on this slide? Okay, the last slide actually comes to us courtesy of my youngest brother's girlfriend, who is currently taking Organic 1 at Texas A&M. I was tutoring her a little bit last night, and we did a kind of a variation of this problem, and I thought it was really useful. So a lot of these reactions are Organic 1 reactions, and then I threw in a couple Organic 2 reactions. But they're all important. So for every arrow, you have to tell me how you would get between those 2 compounds, essentially. So in the first one, we're going from an aldehyde to an alcohol. What reagent could I use to accomplish that? What type of reaction is this? Yeah, this is a reduction. What reagent could we use to do this?
Sodium borohydride.
Yeah, so you could use sodium borohydride. You could also use lithium aluminum hydride if you wanted, but that would be kind of overkill. You only need to use sodium borohydride to get this to work. And then to go the other way from alcohol to aldehyde, what are our conditions?
You could use PCC. No?
Yeah, so PCC or SWERN. Does anybody remember what the SWERN reagents are? Anybody?
Is it the one with dimethyl sulfoxide,
Mm-hmm.
COCl2, I think?
Yeah, so it's this oxalyl chloride. You can also see this written out as that. Just remember the structure is, yep. And then what's in step 2?
Is it just water?
No, we're looking for triethylamine. Okay. So I'm taking the time to write out these reagents because you need to be able to recognize them in a reaction. Okay, so then alcohol to carboxylic acid, how would I do that?
You use Jones.
Yeah, so any of our stronger oxidants. Okay, and then carboxylic acid to alcohol, how would I do that?
Lithium aluminum hydride?
Right. We would have to use our stronger reducing agent. Okay. We have primary alcohol to primary alkyl halide. How would we accomplish that?
Could you use PBr3?
Yep. And then also remember, if I wanted to go from alcohol to chloride, how would I do that?
SOCl2.
Right. Okay. And then halide to hydroxide or to hydroxyl group, how would I do that? Excuse me, it wouldn't be a super great reaction. You'd have a lot of side products, but what could we do? What type of chemistry are primary alkyl halides particularly good for?
Could you use sodium hydroxide?
Yeah. You'd probably get a good amount of elimination also, but you'd be able to do an SN2 reaction to get some of the alcohol. Okay, and then there's this arrow kind of hiding here in the middle, going from alkene to primary alcohol. What would we use for that?
Hydroboration oxidation?
Mm-hmm. Okay. To go from alkene to primary alkyl halide. That's kind of tricky. And we can also draw in another arrow there. Haha.
Could you use HBr and peroxide?
Yes, yeah. You would have to add in the peroxides as a catalyst for some radical chemistry, right? Because it's going to be anti-Markovnikov. Okay, and then to go from the primary alkyl halide to the alkene, what would we do? What
An
type?
elimination reaction?
Yeah, so this is going to be an elimination. What do we want to use in order to get this to happen?
A bulky base.
Yeah. So remember, potassium T-butoxide is kind of our like big favorite from that chapter of OCHEM 1. If I wanted to go from the alkene to the secondary alkyl halide, how could I do that?
HBr at 25 degrees Celsius.
Mm-hmm. Yeah. Let's go from alkene to secondary alcohol now. How can I accomplish that?
Aqueous acid?
Mm-hmm. Okay, and then from secondary alcohol to least substituted alkene, that's going to be really tricky. I probably wouldn't ask you to do that. I'm just going to go ahead and tell you guys what would be your best option here. Would probably be to turn it into an alkyl halide and then to add in just a huge base. That would be your best option. If you tried to dehydrate it with acid and heat, you would not end up with that alkene. You would end up with this alkene. Okay, we're almost done. Secondary alcohol to secondary alkyl halide. Is this any different than what we did earlier to alkyl halide?
Isn't it just PBr3 again?
Yep. And then if we wanted to go to the alcohol, what could we do?
Sodium hydroxide?
Yeah. Since it's secondary, it's going to be a lot more likely to eliminate. So I'd probably do aqueous base to try and promote substitution, but yeah, that wouldn't be a super great reaction. Okay. One more question that I want to add while we're here. Oops, I'm trying to erase, it doesn't want me to. Oh no, okay. Okay, if I were to take this alkene, let's go HCl. What product would I get? Remember, my carbon framework is going to stay the same. Where is the chlorine going to end up? Which carbon?
On A?
Yep. So remember, we would have the carbocation intermediate here. And then we would have a rearrangement. So we would end up with this carbocation. and that's where our product would come from. Yeah, that's it for the end of my slideshow.
Thank you for this.
Oh, no problem. Are there any other questions before we go?
When you said you were gonna post this video, and you said it was gonna be private, are you gonna like send us like a private link or?
Yeah, so I'll send you a link. Anytime that you guys are talking in a video, I don't make it public.
Okay.
So yeah, I'll send out a link to the class, and then anybody who's enrolled in the course would be able to watch it.
Okay.
Okay, anything else, guys? All right, thank you for coming. It was nice to hear from someone.
Sarah.
Bye.